research director. Thank you. He's also research director and president of the steering committee of Centai Institute in Turin, in Italy. He has been president of the Complex System Society and president of the Network Science Society. He's a fellow of the American Physical Society and received the Senior Scientific Award of the Complex System Society in 2019.
A few years after you.
It would take too long to describe the many subfields of complex systems and network theory in which he has made relevant contributions. But these include synchronization phenomena, multi-layer and higher order networks, epidemics, socio-technical and biological systems, and data science. Indicators mean whatever they mean, but as an indicator of his impact, he has more than 50,000 citations. So it's a pleasure to have you here, and thank you for coming. The floor is yours, Yamir.
Thank you very much, Maxi, and everyone for the invitation. It's always a pleasure to be here. And I should come back with more time. This was a good excuse to come here after, I think, 5 or 6 years. So, but I should spend more time here for sure. So thank you for the introduction, Maxi. And yes, what I will talk today about is one part of my work, but is, I would say, the core of my work. I did my PhD in 2000 and was in topics that have nothing to do with this, was some statistical mechanics of fracture mechanics or fracture processes. When I moved to the ICTP, the International Center for Theoretical Physics, for a postdoctoral fellowship, I kind of decided to completely switch and start doing new things. And at that time, networks was kind of taking off. And then I started actually studying epidemiology, network epidemiology. And also this topic is one topic that I usually use as an example when I am asked what has been the contribution of network science into practical problems, to solve practical problems. One very clear example is network epidemiology, which allow us to, track down the evolution of a disease almost in real time today, something that we couldn't do just a decade ago, etc. Another field, of course, is information processing and all related with information, etc. So I will focus on this, and I will kind of use these seminars as an excuse to kind of review not only my work, but the work that has been done in this area. I will discuss two kind of approaches. One is the analytical insights, and the other one is the data-driven modeling of contagion. So the first thing, as we are going to talk about contagion, is to define what we mean by contagion. So for us, a contagion is a process for which a transmissible element, it could be information, an idea, a pathogen in the case of diseases, etc., is transmitted from a spreader to a susceptible receptor. And there are two kind of let's say, contagion dynamics that are of practical interest. One is disease spreading, and this is the focus of the seminar today. But there is also social contagion that is also very interesting and very, it has been the focus of many works in the last few years. Many of the models that we use to study disease spreading could also be used to study social contagion, although there are some important differences between both of them that we can discuss at the end if you want. So the first things that we need to understand is that modeling diseases, modeling today's diseases is not the same of modeling diseases that were centuries ago. This is the example of the Black Death disease. And the Black Death disease or Black Death pandemic started around this area. Turkey, what is Turkey today? Greece, or this area around here. And then it spread to Northern Europe in about 3.5 years. And essentially, this was something that you could model using diffusion equations on a spatial system. And you have wave, front of the epidemics, etc. that you can clearly define. And this was essentially because the transmission was by people that were moving from one small village or town to another small village or town, and they could only do like 20, 30 kilometers per day. So that's, makes that the disease spreads very slowly in time. Nowadays, we are really interconnected. We are globalized, also in terms of how we interact with other people. And that means that the time scale associated to disease spreading has shrunk very, very dramatically. And now we can have spreading or on an emerging disease could become a pandemic in a matter of days, not years, but in a matter of days. Actually, we have recently lived on this COVID-19, which is actually, we are still in the pandemic phase because the World Health Organization has not declared the end of the pandemic yet. But this is not the only one that we have faced in the last 25 years. This is just a representation of different threats that we had in the last, from 1998. So these so-called emerging diseases. And they were, now the monkeypox is rising again, but there were other coronavirus like the MERS, which is typical of the Middle East, around here. Then we have the Zika, the H1N1 or swine avian influenza, etc. We have a lot of this, up to the point that we got COVID. So in these years, we have witnessed the evolution of these emerging diseases. And also with these diseases, we have been able to access an increasingly number of data sets that allows us to characterize the main ingredients that allows you to make your models more accurate and more realistic. One of these data comes from mobility of human, because now we move. Let me just switch off the volume. So we move using these transportation means, and that's why the time scale associated is so fast. But this is just a representation. Each of these points is an airplane. This video is centered around Heathrow in London. But you see that a lot of people are moving around the globe. In 24 hours, you can go from one place of the world to another one. And we are talking about humans, diseases that are transmitted by humans. So if we want to trace the connections, the interactions between potential contacts that could become susceptible into infected people, we should also know about the mobility of these people because they are the carriers of the disease. So this is one data that we have right now, that we have access to this at different levels, not only airplanes. We can also have commuting patterns in cities, in regions, trains, buses, cars, etc. There are a lot of this data. And we also have mobility of humans at the individual level. And actually, I will show some examples in the data-driven part of the seminar, which you have some apps that they are volunteers that give the position, GPS position. So you actually know where any people could be at any time. And then you can build your network of interaction based on that data. So any model that you want to build to explain a disease dynamic process has to at least have these 4 ingredients. First thing that you need to clarify is how the disease is transmitted from host to host. We are dealing with human-to-human transmissions, but of course you can have vectors in between. For example, Zika needs the mosquito to be transmitted. So in those cases, you also need to add an equation or whatever you use to describe your system that tells you how the population of mosquito evolves and how the interactions between humans and people, etc. And in such cases, it's very important to take into account, for example, socio-demographic aspects, because it's shown that the mosquito, for example, normally live in more poor areas because you don't have air conditioners. You normally, in the summer, you open the windows and then you are more exposed to be bit by the mosquitoes, etc. So what are the disease stage? This is also important because this defines the classes of dynamics that you can have in your systems, where susceptibles or infective, recovery, etc. the mechanism of spreading of the disease. So if it's airborne, if it is physical contact like sexually transmitted diseases, if it is by droplets, etc. And this was actually something that was quite a debate at the beginning of the COVID-19 pandemic, because it was droplets, and that's where they were recommending this 2-meter separation. But actually, COVID-19 is airborne disease, so these 2 meters are no doesn't make any impact in the transmission. It's more important to keep ventilation than 2 meters between people, etc. And then this one, which is, I think, the aspect in which we need to work more, because there are some results, but human behavior is essentially something that you cannot control, is something that is very unpredictable, and is something that have a large impact in your model predictions or forecasts. And this is something that we don't really know very well how to model. Of course, agent-based models helps with that, but from a theoretical point of view, we only can make guesses here, because any meaningful behavior that you adopt about humans involves some degree of nonlinearity, and this makes your system more complex, and the solutions also, closer solution, more hard to get. So I will focus on diseases that are airborne diseases. I would not discuss other diseases that could be vector-borne diseases, etc., like Zika, etc. And these are a few examples of these diseases. So I will start with some analytical description of the models, and then at the end I will discuss some data-driven approaches to this. So the first thing is that when you model disease dynamics, you use what we call compartmental models. These are very old models that have been in the literature for quite some time, and specifically these SIR or SIS models are from the 20s of the last century. So these are very old models that assume that you have your population discretized in different states that corresponds to the stage of the disease. So, for example, the two most abundant are the SIR, which means susceptible, infective, and remove. Sometimes you can find it as recover, but the more precise thing is remove, because remove includes people that have recovered from the disease, but people that have died as well, or people that are isolated, or whatever. So people that do not play any role in the transmission of the disease. And then if you don't have to say a removed individual, that means that if you are infected and once you recover, you go back to susceptible because you don't have any immunity, acquired immunity, then this is what is called SIS. This is typical for sexually transmitted diseases, which are normally diseases that you get sick, you recover, and then you are susceptible again to get the same disease. While SIR are more typical of the flu or the COVID, etc. Then you can have more stage or more compartment there, like when you have incubation periods that are meaningful or are significant, then you can have this latency box in which people that are infected but not infectious spend some time there incubating the disease, and then up to the point in which they become infectious. But from a dynamical point of view, these are the two that give you the clues about what are the mechanisms and the evolution of the disease. So to study this compartmental model and the rate of transmission of the disease, what you define is a parameter that is called basic reproduction number, which is the average number of secondary infections resulting from the introduction of a single infected individual in an otherwise fully susceptible population. This is the definition of the basic reproductive number. As you can see, if you imagine this as a branching process, when R0 is equal to 1, you are at criticality. If R0 is smaller than 1, that means that on average you have less than 1 new infected individual, so the process will die out eventually. And if R0 is larger than 1, you are in supercritical regime. That means that you generate more individuals, new infectees than those that were at the previous type step. So the disease, the incidence of the disease will grow up to the point in which you don't have more susceptibles, and then it starts to decline. So, but at the very beginning, and that's why it's called R0 or R0, this is something that is defined as when the total, the full population is susceptible. Actually, this is one of the open problems in network epidemiology, is how to define this for a network system, because strictly speaking, this is defined for a well-mixed population and when it's fully susceptible. But if you imagine, I don't know, R0 equal to 3, you can have nodes with connectivity too, so they are already above the critical, I mean, the R0, etc. So this is one problem that we might discuss, but is something that is defined for homogeneous populations. These are some examples of different values of R0. You can go from values that are very close to 1, like influenza. It's normally between 1.2, 1.4, a typical seasonal influenza. The COVID-19 is not here. Oh yeah, it's here. It was around 3 for the first wave, or the first, the variant, the wild type. It was around 2.53, more or less, but you can have also measles, for example, up to 18 or 19 of R0, which is very, very transmissible disease. And then, as I was mentioning, there could be different routes of transmissions, like droplets, aerosol, you know, some vectors, etc., or airborne disease. So we will work with diseases that are normally with an R0 that is not very, very, very high, is around between 1 or 2, or with the section of COVID that is a little bit larger than that. So as I was saying, this R0 is something that depends on 2 parameters. One that is pure biology, let's say, depends on the pathogens, the transmissibility of the virus, how transmissible it is. Given that there are an infective and a susceptible are in contact, how likely it is that the virus produce a new infected. This is something that depends on the susceptibility of the susceptible individual, or also the transmissibility of the virus, but it's pure biology. And there is another part that is behavior, which is what is the likelihood that 2 people interact. So how likely it is that 2 people share the same space if it's airborne transmit, or that they interact because they are close enough to sustain an interaction for a given amount of time, etc. Where we have, I mean, where the network, the science of network has provided new insights, and we have advanced a lot in our understanding of disease, is because we have been able to deal with this aspect in the last 20 years or so by the introduction of networks. We know that humans are not isolated individuals. We interact as a social beings. So what we need to study is how we interact, how we give, how, you know, collective behavior arrives, etc., which essentially means how we can characterize this network of interactions via mobility data, but also because of, and you know, we also interact at the household, we also interact at the school, etc. So this is the first things that we need to take into account. So I will focus now on the SIS, and I will try to describe it as general as possible, this process, and then we will see different approximations that will lead to consider different kinds of connectivity in the network. You can find more details in this physics report that was published a few years ago. So essentially, we will consider that each individual could be in 3 different stations before. So we will call X, Y, and Z. And these are considered Bernoulli random variables indicating whether the node is susceptible, infected, or recovered or removed at time t. N is the set of individuals. So we can define a Markov change that is essentially composed by the set of space states that gives you how many susceptible, infective, and recovered you have, or the expected number of susceptible spreaders and recovered you have. And what you can write is an equation that describes actually the expected number of, for example, the number of people that are infected in your system. And this is a differential equation that have 2 terms. One is the annihilation term that essentially tells you that with probability delta, all those that are infected will recover because we are in this SIS. So you go back to susceptible states. this other part is the creation terms that essentially codify how likely it is that two nodes K and I interact, and then that one of them is susceptible and the other one is infective. And this, if this interaction takes place with probability lambda, you transmit the virus, and then the susceptible becomes infective. So it adds to this. And then you can calculate the density of infected individuals just summing up and doing the average. So this is the exact equation. There is no assumption here about the network, etc. This is a SAT, but it has a problem. This is 2n equation, because each of these states being random binary variables could be 0 and 1. So you have 2 to the power of n equations that could not be solved for large systems. As n grows, you cannot solve it analytically, but even numerically is really complicated. But you can, but you can get some approximations by dealing with this matrix here that tells you what is the likelihood that two individuals interact. So if you get some approximation for this, you can work out some analytic approximation. This is what other people have done since early 20s, for example. This was by this is the heterogeneous mean field approximation that was introduced by Romualdo Pastor Satorras and Alex Vespignani in the early 2000s. Essentially, what you do is you work with the expected values, but you consider that each individual has, on average, the same degree. So you consider that the average degree of any individual in your population, or the degree of any population of any individual in your population, is a faithful representation of the connectivity. So you can work with the average degree, and this is what we call homogeneous networks. So this means meaningful average degree, and then you approximate this by the average expected value of y, and then you can solve this, and then you find that the critical point is equal to 1, which is verified when the spreading rate is equal to 1 over the average degree of the network. And this is already interesting because you reduce this condition to something that depends on the left-hand side on the biology of the virus, and on the right-hand side on the network of interaction. So this is connecting these two ingredients of the R0 definition. This is for homogeneous networks, and then you can explore what happens with different topologies, etc. The next thing, or the next approximation that you can get, is when the network is heterogeneous, when the average degree is not enough to approximate the connectivity of the individual, and then you are forced to take into account the actual degree of the node. At most, you can classify these individuals in degree classes, what we call degree classes. So I would consider that all nodes with the same degree behave dynamically the same. They are equivalent. And then I have what is called heterogeneous network and heterogeneous mean field approach, in which what you do here is just to work with the actual degree of the nodes. And then this is the probability that is, well, actually I took delta here equal to 1 and substitute, I don't know why, the lambda for tau, but this is the spreading rate. So this is actually lambda over delta, is just divided by delta. So this is the coefficient between the two spreading rates, the spreading and recovery rates. This is the actual degree of the node. This is the probability that the node is susceptible, is 1 minus the probability or the expected number of infected individuals in your system. This is the probability that the node of degree k is connected with node of degree k prime. And this is the expected number of infected individuals of degree k prime. This will give you the evolution of the number of infected individuals of degree k. So you can perform some stability analysis. I wouldn't talk too much about this, but essentially what you get is that this spreading rate should be larger than the largest SM value of the agency of this connectivity matrix, that is this one around here. This CKK is the largest in value of this K, P, K prime, K prime. So this is the result that you get, which when you don't have any correlations between K and K prime, so the probability that a node of connectivity K is connected with a node of connectivity K prime doesn't depend on K prime, you get this classical result, which is the result by Pastor Satorras and Vespignani, that tells you that if you plug this into this, that the spreading rate is should be larger than the coefficient between the first two moments of the degree distribution. So the average divided by k squared. This is the second moment of the distribution. So that means that if you have a power law with an exponent between 2 and 3, the average degree is finite, but the second moment of the distribution diverges when you take the thermodynamic limit, because in that case, the second moment of the distribution is not bounded. It grows as n tends to infinity. It also diverges to infinity. And this is, let's say, the classical results that we can recover from this previous approximation. So you can also do other kind of approximations, like, for example, considering correlations and giving some form for these probabilities, or you can measure this from real data and then plug it into your equation and solve it numerically, and this is something that you can do. Anyway, up to now, what we have been focused is on this tau, but let's suppose that we want to also know what is the probability that a given node is infected at any given time. So for that, these sort of approaches are not useful, because you are classifying it by degree classes, and on the other hand, you are working on the stationary state, so you don't really know what is the probability that a node of degree k is infected at that time. For that, what we are going to introduce is a more general kind of microscopic approach, which on the other hand also takes into account something that up to now we haven't noticed, is the fact that even if your set of contacts, let's suppose that you have this degree, this is your degree k. So that means this is the maximum number of different nodes that you can contact, but that doesn't mean that you need to contact them only once and all of them at the same time. So in principle, for example, you in a typical day, you can contact only 4 of your the people that you have in your social cycle. For example, maybe you contact here your teamwork or your teammates or whatever, or a household, the people that live with you, etc. So this number changes from time to time, and it's not always the maximum number of contacts, because when you measure this is normally aggregated over time, but that doesn't mean that you contact everyone only once any given time. And you can also have these sort of situations in which you can contact people more than once during the time interval of interest, and in that case you will have a weight associated to the link. So it's more likely that you contact this individual 3 times, or this one, or whatever. So the question is, well, in this case, when the number of contacts that you effective contact that you do in a given time window is not homogeneous, or is not equal to the maximum number of contacts, how to cope with this, and whether this allows you to say something about the probability of one single node to be infective. So what we did was to propose this kind of discrete Markov change approach. I don't know if you have heard about this, because Sandro was involved here, and I think that maybe he has given some seminars here. But essentially what you write down is this equation that tells you what is the probability that given a node I is infected at time t plus 1, and this depends on the state of the node at the previous stage, so whether this is it was susceptible, and the probability that it's infected, it was infected but recovered, or it was infected, recovered, but was infected again. So it was infected but didn't recover, and it was infected, recovered, but it was infected again. For this, to calculate this, what you calculate is actually the probability of a node not being infected at any time by any of your neighbors. And this is simple, this expression here, where this RJI is not the contact, the adjacency matrix, but is what we call a contact matrix. And this is easy to see that the functional form of this is this expression here, which essentially deal with, I mean, you treat this problem if you have a node here and you have a set of neighbors that you have to contact. This is the number of contacts per unit time. So if the number of contacts per unit time is equal to 1, this is a contact process. You contact only one of your neighbor, and you do it proportional to the weight of the network. So this is I, J, L. So this is, so you do it proportional to the weight of the edge. If, on the other hand, this K is infinitive, you are sure that you will contact all your neighbors. And in such a case, these are Ij is equal to the adjacency matrix. Only in this case is actually equal to the adjacency matrix, because when you launch an infinite number of random walks, let's say, to contact your neighbor, you are sure that you will eventually contact all your neighbors. Only in that limit is when these two are the same. So this is actually a family of models that depends on these contacts per unit time. And what we do is, okay, once you have this, then you can work on the stationary state limit, because this is SIS. So you know that there is a stationary state. And then this is a fixed point equation. You can get rid of time. And this is a fixed equation that you can actually try solve to find the threshold. And the idea is that in the threshold, when you are close to the critical point, the probability of getting infected is very small. So you can approximate this product by the summation. And after that, you can rearrange this equation as an eigenvalue equation, and then solve to find the largest value of this Rij matrix, because it's the only, so this system has a solution if and only if this is an eigenvalue of R, and then you find the same result that we have before, which is that this critical point is 1 over the largest value, but in this case is not of the adjacency matrix. In this case is of this Rij matrix. That again, if it is not correlated, not weighted, undirected, you recover the result that the largest value is the ratio between the two moments of the degree distribution. Numerically, you can solve, and you can show that these are the probability that node I is infected at the stationary state. This is the solution of the fixed point equation, and these are Monte Carlo simulation. And you see that this is in the diagonal, so which means that your model is able to capture also at the individual level the dynamics of the disease. And this is the average number of infected individuals as a function of the transmissibility. And you already see that depending on the number time, your incident change as for a fixed value of beta. So if you place yourself here, you see that depending on the number of contacts per unit time, it's the incident change. And this is something that it's at the root, let's say, of the measures that we take to reduce the number of contacts. So when we say, okay, let's reduce the number of people with whom we interact with during an epidemic, the idea is to reduce the number of contacts per unit time, because we know that if you reduce the number of contacts per unit time, the incidence of the disease will go down. And this is kind of also coming out of these analytical kind of insights. So far, I kind of have revised the network epidemiology when we consider that there is only one network. But when you study real networks, you realize that we have more than one network usually at some time. So normally we have different layers of networks that are interacting. Or if you want, the dynamical process itself is not only the disease that you are studying, but this disease could be also influenced by other processes that are going on. And for that, this framework, that multi-layer network, is very useful to study the case in which you have interacting diseases. So when you have interacting diseases, the idea is to say, okay, let's study diseases when you have more than one disease, so diseases that are concurrent to each other, the presence of one disease impacts the evolution of the other disease. So essentially what you have is a host population and different diseases that could be any number of diseases, but that the mechanism of transmission is different. So the network of contacts does not necessarily have to be the same. So you are this individual here and you are this individual here, but your contacts are not the same depending on the disease. And one clear example of this is the interaction between tuberculosis and HIV. It's a very clear example. If you want to understand the dynamics of these two diseases together in a population where the incidence of this disease is high, both diseases is high, you need to develop coupled models because the presence of one disease affects the evolution of the other disease. And this is, and the network of contact is not the same because HIV is a sexually transmitted disease with a network of contacts that is completely different to the network of contacts for the transmission of tuberculosis, which is an airborne disease. So for the sexually transmitted disease, you need physical contact. For the other one is more airborne diseases. They are very correlated. This is what data tells you. This is the situation of, so in color is the tuberculosis incidence, and the percentage shows the HIV incidence. This is 1990, when the HIV was just arising globally, not only in Africa. But then, and this is 15 years later. So only 15 years later, you see that the incidence of the tuberculosis grew by 70%, 60% or more in some countries. And this is the more than 400, so multiplied by kind of with respect to 2 by 2 or 3, factor 2 or 3. And the incidence of HIV was 70, 60, etc. If you plot these numbers and do a correlation analysis, you see that the growth of the incidence of one disease is perfectly or is very well correlated to the growth of another disease. So in this case, you need to study both diseases concurrently to each other. Another example that in this case is favorable to us favors or impede the disease, because this is what we call cooperative diseases, this tuberculosis and HIV, but in this one is competing diseases. They could also compete, and one disease could confer some degree of immunity in front of the other, or for any other reason prevent the transmission of the other. And this is the case, for example, of COVID and influenza. This is the number of influenza cases per year. You have the typical peak around January or February of every year. And this is 2021, 2020, 2021. Almost no flu reported those years. And this is direct effect of the measures that we took for COVID-19, which prevent also the transmission of influenza. So if you don't take that into account, you will expect from your models another peak here, which is not actually there, just because there is other disease concurrent to yours that somehow impedes the transmission of the other disease. Essentially because it reduces the number of contacts, because you adopt measures for the other one that have some impact on this. All of this you can do in a model, essentially, that is a multi-layer system in which you have the same individual, but could be in different states. So you could be susceptible or infected to in front of disease 1 or susceptible infected to disease 2. So you have now not only 2 states, but you have 4 states, and these are the transitions, etc. This could be solved analytically, using also the heterogeneous mean field, etc. But numerically, I will show you what happens. So what happens is this is disease 1, this is disease 2, and this is the initial state. We are in the case in which there is mutual enhancement. So that means that the presence of one disease favors the spreading of the second disease. And we are also considering homogeneous patterns. So at the very beginning, you introduce disease 1, and this is the classical threshold that you get. This is threshold of disease 1. So you said that if you are to the left, there is no outbreak. If you are to the right, there is an outbreak and the incidence, etc. Of course, disease 2 has not been introduced yet, so it's not present. So let's suppose now that we introduce disease 2. So when we introduce disease 1, the fact that there is also another disease here makes that the threshold of disease 1 is smaller than what it would be if this disease was not present, because what you will expect is this threshold here regardless of disease one, this will be constant if there is no disease one. But the fact that there is a disease one, when it kicks off, then this threshold is smaller. So this is what epidemiology is called secondary threshold. It's completely due to the presence of another disease. So you will expect this to be around here, but actually the area in which your population is exposed to the presence of this other disease is enhanced, is larger than before. And of course, eventually, this second disease also have an impact on the disease, on the first disease, because it also reduced the threshold for the first disease. Not only the threshold, but also the incidence. So this is what happens there, etc. Just to mention that this is something that you can also use to study social system, because instead of talking about diseases, you can also talk about Facebook or Twitter, etc. So social networks, and each layer will correspond to one of these social platform or whatever. I wouldn't enter into details, but the microscopic macro change that we described could also be generalized to the case of multi-layer networks. The only difference is that now, instead of working with the previous equation, you have to specify that this is the probability that node I and J interacts in layer alpha. And this is the number of contacts per of node I in layer alpha. This is something that you can still solve and using the same approximation as before. And you find that the critical property of the system are defined by the largest value of these are supra-adjacency matrix, supra-contact matrices. This is the largest value of supra-contact matrices. You can go a little bit further and say, okay, but how the largest value depends on the properties of this layer, and then you can do sort of perturbative analysis, and you can show that at first order, the largest value of the multi-layer system is equal to the largest of the largest values of individual layers. So that means that even if you have a multi-layer system, there is only one layer that sets the critical property of the full system, and it's the one with the largest of all the largest values in your system. And this is also interesting because, as we noticed, this depends on the contact rate. That is something that depends on the layer. So this gives you already something to play with, which is, okay, let's suppose that I have two layers. Let's suppose that layer one, the largest value of layer one is, let's suppose, lambda 1 equal to 10. And then I will tune the contact rate in layer 2. And if I change this value, I am changing my matrix, so I am changing also the spectral properties or the largest value in particular of this matrix. So if I play with the lambda 2, I will play with the largest value of the second layer, and this is what is represented here. So I start increasing this lambda 2, and then the largest value associated with this layer start to increase, and that means that at some point it crosses over the previous one, and then here up to here, layer 1 was the dominant layer. From this point on, the dominant layer is lambda, is the second layer, because it has more activity, or the largest value is larger. And if I eventually increase this, then this will be again the dominant layer. And especially if I, for example, put here 32, that means that this never turns into the dominant layer. So this is a very naive interpretation. I'm not comparing with real data, but this could explain why when you analyze a social system, sometimes there is a platform that is kind of more dominant in spreading some kind of information than others, and this might be because the spreading rates in those layers are changing in time, and then that means that at some point there is one dominant layer over the other, etc. Yeah. Sorry? 1 minus in your equation. Oh, here? This in the bracket. Yeah. Yeah, this is no. This could be any. This is the number of contacts. In the bracket. This one. Oh, yeah. This one. Yeah. 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 Yeah, and then this would mean that this is the adjacency matrix. Yeah. Yeah. No. Yeah. But no. But this depends on this. So if this is 0, this value is 0. So if you don't have any connection between I and j in layer alpha, this is 0. Is 1 minus 1. So whatever the exponent gives you 0. So yeah, for any value of this different than 0, then it's 1. Okay, so up to now, this is theory, and I will use my last few minutes to discuss some data-driven models. And the first thing that I want to notice is that when you analyze real epidemics, things are really more complex than what I showed you right now. And this is essentially because humans have a role in the transmission. And humans are essentially something that you cannot control or predict very accurately. And to show that, I will use this example of an experiment that was done in UK in a department. I think it was a mathematics department in a university in UK, where you have a room like this, but also with coffee and tea machines, etc. So it's or the room like the one that you have on the second floor, where you can meet people, interact, etc. So participants were serving coffee or tea, and then if you can put milk on the coffee or the tea, and if you put milk, you have to pay a fixed amount. Let's say, I don't know, 10, 20 cents, but you are free to choose where to pay or not. So if you pay, it's 20 cents, but you cannot pay. You can play, the defector and not play. And so in front of the dispensers, they have an image. Every week they put an image. It's a poster like this one with this. They were collecting the amount every week, and they were measuring the correlation between the amount collected and the image that was there. And what they found is that actually humans can be fine-tuned. So maybe you can try this in Maxi here. And you see that when you see eyes and not flowers, the average collected amount is larger than if you see flowers. So this is a very simple example that shows you that our environment influences a lot the decisions that we make. And this is, when there is no threat for you, this is just a poster. It's not even something on a screen that moves, etc. It's very simple experiment. Imagine when you are in the middle of the pandemic and you have to make decisions based on a lot of information sources, etc. So that's what makes predictions very, very complicated. Just for you, well, you know the numbers, but this was the last data that was collected by this Johns Hopkins University in March 10, and the number of reported cases verified was 676 million globally, with almost 7 million deaths and 13.3 million billion vaccinations around the globe. So let me also say, because unfortunately, there is this misconception by people that are not used to do epidemiology about what is forecast and what is projection. So usually when you do a forecast, what you do is unconditional. So you have your model and you don't assume anything, and then you run your model and you predict the incident, for example. Normally you can do it only for a time window that is 2-3 weeks at most. It's helpful because it anticipates needs, like, for example, if you predict the incidents or forecast the incidents, you can kind of anticipate your needs in beds, etc., in the hospital, etc. It is more accurate when R is not very large, because otherwise the non-linearity is increased, and then your prediction is not very good, etc. And it's useful to detect behaviors, provide insights, etc. But this is something that you can use. But when someone asks you about what to do, this is not useful anymore, because you need to take then into account conditional specific scenarios. And that's what we call projection. Happened if, and this is not a forecast, is a projection that you can do on a much larger time window. You can use to anticipate trends, outcome of decision, but more importantly, it's not a forecast. It's something that provides interpretation of what if a scenario, and actually is usually something that you don't see in the data, because what you say is, if you do this, this is what you are going to get, and normally whoever is the decision maker say, okay, I will not do this because otherwise my situation will worsen or whatever, and then you don't take those measures. So it's something that you usually don't see, precisely because you were able to project the situation, and then you didn't adopt those measures that will have produced the prediction that the projection that you did. So it's just to clarify, because there is this thing. So what I'm going to show you is one example of projection, how we project. And this was a work that we did in April 2020, when we were in the lockdown, and there was the need to evaluate possible measures to open up the system again. For this, what we did was an agent-based model with a data-driven approach that essentially built a sort of synthetic population that was statistically representative of the Boston area. So this is Boston. So we took this and we used data that was provided by Quebec. I think Ramasco has used those data, etc. Essentially, is an app in which people voluntarily register and provide their GPS localization. So each of these individuals you have geolocalized. So you can build a multi-layer system that essentially you can divide in 3 or 4 layers. One is the household layer, the other one is a school layer, and this is divided like this because it's very known. You have a statistics to reproduce the size and number of students in school, etc. And with Jorge, we did this sort of approximation for 5 cities in Spain. And then you have what we call workplace plus community layer. If you have data about workplace, you can actually split this in 2. And the community layer is the layer in which you include all random encounters. So when you go to a restaurant, so you don't, it's usually the kind of interactions that you don't remember. If someone asks you who have you interacted with, normally you say, okay, I have these people in the seminar today, etc., but I don't remember who was next to me at the breakfast in the hotel. So this I cannot report, and I usually put in the community layer and assume that these are random contacts. When you have GPS, you have the geolocalization of the 2 individuals, so you can assume that if 2 individuals are close enough for certain amount of time, you will consider that this is eventually an interaction. And then you start building your network of contacts. On top of that, we developed a model that is more fit to describe the real COVID. It's not, it's sort of SIR, but it's more complicated than that because we have asymptomatic branch, symptomatic, and depending on whether you were asymptomatic or not, or pre-symptomatic, the probability of getting infected depends on that. So if you are asymptomatic, this R is normally smaller than 1. This one is the beta, the transmissibility, the typical one, and this is the symptomatic. Pre-symptomatic is a different one. So, and then you have hospital, ICU, etc. As we have the geolocalization, this allows you to evaluate the scenario, to do this projection. And essentially, we develop 3 scenarios. This is the baseline. This is raw data, the data that we have that was collected in February and March. previous lockdown. So as you have the localization, you can then assume a medium closure, let's say, which is, okay, let's close all restaurants, churches, sports centers, gyms, etc. And I will remove all contacts that are in those places. So my network is reshuffled and it's done. And so the number of contacts, this was the distribution of the baseline, reduced to this distribution. And the average here was around 50. The average here is around, I think, if I'm not wrong, around 18 or something. And you see that the number of contacts was reduced by 30%. From here to here. Essentially, you close all schools, and then you reduce a lot of interactions in the community here. And then the non-essential closure is, okay, I will just keep open the very essential places, hospitals, some delivery places, etc. And this reduced the number of contacts by 90%. And here the number of contacts is about 5 to 6, the average number of contacts. So what we did was to implement on top of this synthetic population these 3 scenarios, and we see, and then we try to see what kind of measure could lead you to a safe opening. So the first thing to note is that if you do nothing, this is the baseline scenario, the peak is huge, the incidence or the prevalence then is more than 75% of your population will be infected. And this is the R0 that you see is up to 4, the RT, because it changed on time and then declined, etc. So it's a very fast spreading, but the cost that you pay is really huge because 75% of the population is infected. So the 2 scenarios that we evaluated was, okay, let's do a partial reopening, and then we completely open. There is no tracing, contact tracing, and there is no isolation or quarantine of individuals, etc. So, of course, what you get is the same as you will expect here, because I insist on this because there are also some misunderstanding on this. The disease dies out because you don't have susceptible, not because you don't have infected. So when you solve the equation, this peak there, when R start to be below 1, this peak is because of the lack of susceptible, not because you don't have infected, because actually it's when you have the most infected in your system. But then you run out of susceptible, and then it starts to decline. So this is important. So when you open here, if you don't do nothing, you have almost the same susceptible population with also others infected individuals there. So you shouldn't expect anything different. There would be another peak, etc. The difference here, it wouldn't reach 75 just because you keep a school closed. And that's the only difference why this doesn't go to 75%. But other than that, you see here, etc. So the scenario that we suggested and that was given the best result was tracing and quarantine. So the first thing that you do is partial reopening plus quarantine of the positive cases, and then you can do total reopening. This is what you get for 20%. So for no tracing, this is for 20% of tracing, contact tracing, and this is 40% of contact tracing. And you see that also the time scale change, because again, you still have susceptible individuals. So what you are doing is actually spreading out the evolution of the disease in time, but at the end of the day, you see that the prevalence is more or less the same that you will get here, except some minor changes in the percentage, etc. But this is the safe way to evaluate, to open your system. The cost that you pay is that the disease is running for a longer time. So here the disease will have, die out in July or June. Here in December 2020, you should have still the disease. And actually, we still have it. In terms of, this is my final slide. In terms of occupation of beds, we also have some data on the Boston area of the number of ICU units available and ICU beds. And this is what happens with hospitalization, and this is what happens with ICU beds. So this is the level when you increase it. So you see that if you do detection with positivity rate of, with accuracy of 50% and contact tracing of 40% of the people that are in contact with any given positive, you are below the ICU capacity. So you can handle the situation. And this does not come at the cost of quarantining the whole population. So if you see here, what is the number of quarantine households at the peak, it would be around, for 40% of traces, it would be around 10%, which is much less than having the full population in lockdown. So this actually is worked. And in countries like Korea and Japan, etc., that was the thing that they followed, and actually they didn't do a lockdown as we did in Europe or in the US. Just to finalize, just to mention that if you can do this, we also have some data about this community layer. We have daily data, so this could be also another multi-layer that could be a temporal multi-layer in which the number of contacts per day change, and then you can, ask questions about what happens if I implement a measure on this day or on this day or on another day, etc. And just to show you that the results work, this is predicted prevalence or projected prevalence versus the prevalence measured by serology. And you see that this is reproduced pretty well. Okay, so finally, I didn't have time, but I will just leave this open. And is up to now, we have discussed single layer, multi-layer, but one of the things that I think is really kind of hot topic in network science right now is higher order interactions, in which you don't consider anymore that two individuals could interact following a pairwise interaction, but you consider that actually many interactions occur in groups. So in group interaction, so does not codify only pairwise interaction, but is a group interaction. So this is what is called hyperedge. And this hyperedge, for example, encode the interactions between these three. And so if you write the set of vertices and the set of edges, you see that they are completely different, because here you have triplets or four nodes, etc., etc. It has been shown that this introduces very rich dynamical behavior, especially when you analyze social contagion, because this is now a critical mass dynamics, and then you get very rich behavior in terms of phase transition. For example, you could have hybrid or first order phase transition when where you had before second order phase transition for pairwise interactions. I'm sorry for taking more time than what I was expecting, and these are the final thought about what I think could be interesting. I think that this higher order network is important, and from the epidemiology of real system, how can we account for human behavioral changes is also another important, which, by the way, is something that there are people that are starting to explore this using what is called generative IG basic models. So instead of using humans, you can use large language models and ask them to react to the presence of the disease and see what happens when you have this sort of thing. My collaborators and funding, and thank you very much for your passion.
Thanks very much, Amir, for this very complete overview of the field. Now, questions and comments? Anyone? Was to complete? No.
Comment. With respect to the correlation you made between influenza and COVID, it's a little tricky comparison, because at the end you prevent them because you are using the mask or you have the lockdown. So you could apply the same idea only for influenza and it would work without the COVID, right or not? So why do you call that these two diseases are correlated with each other?
Well, actually, yeah, maybe I didn't explain it well. It's not that I think that these two diseases are correlated. What I mean is that the presence of one disease affects the evolution of the other. Maybe not because of the disease, but in this case, because of the measure that you adopt. And this was also, this is the case also for tuberculosis with COVID. So it's not that COVID makes tuberculosis worse, it's that tuberculosis needs long treatments. And when you are in lockdown, you cannot go to the hospital to take your treatment. In Spain or in Europe, yes, but not in Africa when you have to, walk a lot of kilometers, etc. And it has been shown actually by data that the rate of diagnosis have decreased a lot, and this has induced an increase in the incidence of tuberculosis after COVID.
Can you use some causal measurements instead of only correlation to detect more precisely one effect on the other?
Probably yes. We haven't done, but probably yes. One thing that we use, well, yeah, I think, yeah, it could be something that you could do. Yeah. Yeah.
Could you mention or point out just based on few or basic differences between the spreading of a disease and the spreading of a rumor on social media? The basic difference between the two things?
Yeah, the basic difference is that the disease, well, to start with, the disease, you have to reproduce the incidence curve. When you have a rumor, you can be forced to reproduce the measurement that you have from your system, but you can also design a rumor. If you want, for example, to design a viral marketing campaign, you can design your rumor. So you can design your spreading mechanism. But from a fundamental point of view, the main difference is not in the creation term, because it's exactly the same, it's in the annihilation terms. For disease, the likelihood of recovering, so you go to the R class, is simple, the recovery rate plus the density of infected individuals. For the rumor, what you have in what we call a stifler is that you go there with a probability that depends not only on this, but depends on the interactions between these two. So it's not a spontaneous recovery anymore, but depends on the interactions between what we call, in this case, a spreader and stiflers are essentially. So because when you do the rumor, it works like I call you and I tell you, oh, the Nobel Prize yesterday were for these two people that were foundation of machine learning, and you tell me, oh yeah, I know. At that point, I start thinking that maybe the news is not new anymore. And then the next time I call Maxi and tell the same, Maxi say, oh no, I know again. So at that point, I lost my interest in spreading the rumor. So I cease spreading the rumor and I turn into a stifler. So this turning into a stifler is a result of my interaction with the other. And this makes this annihilation term nonlinear. And that makes the problem also interesting, but harder to find some analytical solutions. I think this is the most interesting difference or the fundamental difference between rumor and disease dynamics. Disease, you recover spontaneously or because you take treatment or whatever, but it's something that does not depend on your interactions, while rumor is something that depends on your interaction with others.
More questions or comments? Tobias?
So Doyen Farmer has this nice example of predicting the weather. And he said sort of up to recently, it would be much better just to ask somebody who knows about the weather, a meteorologist, say, what do you think the weather will be like tomorrow? And then people came up with models, and it took, I don't know, 30, 40 years to develop these models, and they're just about breaking even, or maybe have now slightly overtaken in predicting what the weather is, right? So how do you see this here for predicting, whether a certain rumor will spread or a certain disease will spread?
Oh, yeah.
How far away are we from better ask somebody, ask Fauci what he thinks, or use these models?
Well, I think that, there is an important difference between the two things is when you predict the physical system, the evolution of physical system, that prediction would be your prediction if your model is correctly, regardless of what humans do. So the hurricane will not change the trajectory if people are leaving the city or not. When you do a prediction in disease, people know the prediction, so it's a self-adaptive system in the sense that there is a feedback between the information that you provide and the change of behavior of the individual. And that makes prediction usually not observable. in some time window. That's on the one hand. And to be close to what we have in weather system, we need more sensors. So essentially, all this data-driven simulation depends a lot on your capacity to measure the position of individual, mobility of individual, or during a pandemic, the incidence, the number of cases per day, the new number of cases per day that allows you to define your reproductive number, etc. And this was chaos at the, in the COVID-19. So there was, I didn't talk about this, but there was this recommendation about, I mean, the strictest lockdown in Spain, when you look at the data, was actually not needed. You could save that. These 2 weeks that we were actually in the strictest closed down was not actually needed, because the recommendation was based on the evolution of RT, and this evolution of RT was not using the number of symptomatic case reported, but the incident. And the incident has a delay of about 2 weeks, depending on the autonomous community. When you use the right data, you notice that when it was implemented, the stricter lockdown, RT was already below 1. So if you use the wrong data, it will tell you that RT was still above 1, but if you use the proper data, it will tell you that it was already below 1, so declining. So that was not really, from an epidemiological point of view, was not really needed. And any claim about we need this lockdown, strictest, etc., is unfounded if you use the proper data. And that's a result of having a system that was not prepared to handle those reported cases, etc. So I think that's the main things to do. The main things to do is to work on, I mean, if you look at Seoul, Korea, how they manage the disease, they have this Middle East coronavirus in 2015, the MERS, and when they faced that, they were able to control that, but they learned a lot about this. So at that point, they changed the law. So in pandemic situation, they can trace you using public CB systems, etc. And so when someone is reported positive, is traced to this store, and in this store they recognize with who they interacted with, and they do a contact tracing very efficient. They also created an institute for something like CDC, but for disease with around 300 staff that are devoted to that. Educated the population, etc. So, and created a scientific advisory committee to the government, something that we didn't have in Spain. Not in Spain only, but in many countries in Europe, we didn't have that. So they were very well prepared for that. We didn't. I'm afraid that we haven't learned the lesson, and the next pandemic, we will face the same problems.
Yes, last question.
More of a comment than a question. Okay, one thing is the data. I fully agree with you that even in the COVID pandemic, there were different styles or regulations for reporting COVID deaths in different countries. So some hospitals would report them on Mondays, some would be reporting on Fridays, there's weekly seasonality. And there's a lot of issues with that. So unless we have really good quality data, there's not much of we can do in forecasting. And regarding forecasting, since I'm a forecaster essentially, your distinction between unconditional and conditional, well, I wouldn't agree with this, because the forecast is actually a conditional forecast. It's conditional on the information you have at this moment.
Yeah.
So is it called a forecast or predictions, more or less the same? They are synonyms essentially. The projection is also called a simulation or scenario simulation. And you can have interventions, like in economics, different interventions. So what you are essentially doing here in the paper, I understand, you are analyzing the impact of some interventions on the system.
Yeah.
And the effect is you do not have a distribution of the variable that you are looking for, but this is kind of, if this and this happens, then this might be the outcome.
Yeah.
But you cannot say much about the distribution. So the distribution of the variable that you are modeling is the main distinction between a forecast and a projection or a simulation.
Yeah. No, what I mean unconditional means unconditional to a scenario evaluation. So it means that, yeah, but of course you also have a distribution of the variable, etc. Yeah.
Okay, I think we need to finish here. So let's thank Yamir again.
Thank you. Thank you very much. Gracias.